Okay, let's get started on hypothesis testing. And hypothesis testing has a standard procedure of 8 steps to prove a claim or statement. Procedure. Proof 8 steps. To prove claim. Or hypothesis. So we're going to develop the ability to conduct hypothesis testing for claims made about population proportion P and also the population mean mu. Okay. So we're going to concentrate on proving population proportion P and population mean mu. Following are the examples of hypotheses that could be tested. First one is about genetics. So the genetics IVF Institute claims that its exome method allows couple to increase the probability of having a baby girl. So this is a claim you try to prove or you try to verify. Second one is about business. A newspaper cites a pricegrabber.com survey of 1,631 subjects and claim that majority have heard of Kindle as an ebook reader. Third one's about health. Biology field. It's often claimed that the mean body temperature is 98.6 degrees. We can test the claim using a sample of 106 body temperatures with a mean of 98.2 degrees. And when conducting a hypothesis test, you should focus on the context of data, meaning how do you obtain the data or original source of the data, and also the sampling method used to obtain sample data. You make sure it's randomly selected and with a good source of data. In this particular section, we're going to concentrate on different elements of hypothesis test. First one is how to identify the null hypothesis and the alternative hypothesis. Null hypothesis is using HO, alternative hypothesis H1 for a given claim, and how to express in both symbolic form. And we're going to learn how to calculate the value of the test statistics. You can use this symbol, either T test or Z test. Okay. Given a claim the sample data, and then learn how to choose a sampling distribution that's relevant. And then learn how to identify p-values or identify the critical values. Then eventually we state a conclusion about the claim in simple and then non-technical terms. That's basically the main issues we're going to address in a hypothesis test. So a hypothesis is a claim or statement about the property of a population, or you can also say this is a test about the population parameter. And a hypothesis test is the standard procedure for testing a claim about a population parameter. The property of a population is what we call population parameter. We test the validity of the population parameter. So this is a random event rule. We talk about it in chapter 4 of probability for inferential statistics. So if given under a given assumption, the probability of a particular observed event is extremely small, then we conclude that the assumption is probably not correct. Meaning when the probability of certain event is very small, extremely small, that means this event is probably unlikely event. Unlikely event means it does not need to happen. Okay, and this is the guiding principle for the p-value method. We'll talk about hypothesis testing. So we start with the null hypothesis. Again, we use HO to represent null hypothesis, and also null hypothesis always have equal sign. So let me give you some example. Null hypothesis HO could be population mean equal to, let's say 10. Okay, this is first way. Second, HO could be mu greater or equal to 10. Third case would be HO mu is less equal to 10. Again, if you observe all these three scenarios, null hypothesis all have equal sign there. Okay, equal to some claim values. We test the null hypothesis directly in the sense that we assume it's true and then reach a conclusion to either reject HO, or fail to reject HO. Okay. So the null hypothesis is the main focus in the hypothesis testing. I always have the equal sign. Now let's move on to alternative hypothesis. We typically use H1 or HA. And from now on, we're just going to use H1, the statement that the perimeter has a value that somehow differs from the null hypothesis. And the alternative hypothesis has no equal sign. So the alternative hypothesis, first scenario, H1 could be mu is greater than 10. Okay. Second scenario, H1 could be mu is less than 10. Third scenario is mu is not equal to 10. Okay, so either one of these could be an alternative hypothesis. Again, the common characteristic here is there's no equal sign. So forming your own claim, you basically, first step, forming a claim, so you set up HO and H1. Okay. Come up with a statement about HO, statement about H1. So if you're conducting a study, you want to use the hypothesis test to support your claim. Claim must be worded so that it becomes alternative hypothesis. There's three simple steps to identify HO and H1. The key thing is that H1 has an equal sign. No equal sign for H1. So specific claim, identify a specific claim or hypothesis to be tested, put in a symbolic form. Give a symbolic form that must be true when the original claim is false. Of the two symbolic expressions obtained so far, H1 not containing the equality. So H1 could be either one of those, greater than, less than, or equal, not equal to. HO is a symbolic expression that perimeter equal to fixed values being considered. So it always has equal sign here. So it could be equal to, greater, equal to, or less equal to. Assume that 100 babies are born to 100 couples treated with XOR methods of gender selection. Let's claim to make girls more likely. We observe 58 girls in 100 babies. So again, this is a sample. It's like getting a girl is a success event. Girl, having girl, success event. You again go back to binomial probability distribution. Having a boy, failure event. And they are neutral, right? Success and failure are neutral terms. So now here we have 100 newborn babies. This is a sample. So in this case, we know that sample proportion p hat equal to 58 over 100. So this is turned out to be 0.58. And write a hypothesis test to claim that with the XOR method, the proportion of girl is greater than 50% that occur without any treatment. And this one greater than has no equal sign, then we know that this must be an alternate hypothesis. So here we identify the alternate hypothesis. So the claim here, alternate hypothesis first, HO, H1. H1 definitely is going to be population proportion P greater than 50%. And here, HO must be P equal to 50% with the equal sign. Okay, so that's how we state the nominal alternate hypothesis in this particular case. And step number 4 is select a significance level alpha. So you could have 95% confidence, then significance level alpha equal 0.05. 95% confidence level. You could have 99% confidence level. Then the alpha equal 0.01. This is alpha. Depends on different confidence level. So the significance level denoted by alpha is the probability of test statistics falling in the critical region when the null hypothesis is actually true. So basically, for that case, it's right tail test. So this on the right tail here, this is what we call the critical region. Critical region is also called a rejection region. So if the test statistics fall in the rejection region, then we reject HO. This is the same alpha introduced earlier in chapter 7. Common choices alpha is 0.05, 95% confidence. 0.01 is 99% confidence. When alpha equals 0.10, then it's 90% confidence. Okay, and then we move on to step 5. Then we start to identify the test statistics and determine the sampling distribution. So test statistics, if you're testing for population proportion P, so use a Z distribution, normal distribution, requirements NP greater than 5, NQ greater than 5, and the sample is a simple random sample. So the test statistics, Z-score equal to P, sample proportion P hat minus population proportion P, dividing by square root of PQ over N sample size. And if we're testing for mean mu, in this case, when sigma is unknown and normally distributed, we have a normally distributed population of sigma unknown, sample size is greater than 30, then we use t-test. So test statistics t-score equal to sample mean minus population mean over sample standard deviation over square root of sample size. And we're testing for population mean mu, given that with the normal distribution we're using z-test. When the population standard deviation known, we have normally distributed population or population standard deviation known, and the sample size is greater than 30. Then test statistics z-score equals sample mean minus population mean mu over population standard deviation over square root of sample size. We're not going to do standard deviation of sigma variance sigma, so we're going to skip the last one. Okay. So the test statistics is a value used to make a decision about a null hypothesis. And it's found by converting the sample statistics into a score with the assumption that null hypothesis is true. So it's either turn it into a t-score or z-score. Z-score, okay. And step 6, find the value of the test statistics then find either the p-value or critical value. So there are two methods. Method number one is using the p method, meaning find the probability associated with this given test statistics. Method number two is critical value method. So first of all, we transform the relevant sample statistics to standardized score called the test statistics, and then find the p-value or the critical value. Let's again take a look at the claim that the XOR method of gender selection increases the likelihood of having a baby girl. Preliminary results from a test of the XOR method of gender selection involved 100 couples. It gave birth to 58 boys, and then 58 girls, and then 42 boys. Okay. Here's the given claim that preliminary result to calculate the value of the test statistics. Again, here we know the p-hat is 58 over 100. 58 girl over 100 babies, 0.58. Using the given claim that preliminary result to calculate the value of test statistics, use the format of test statistics given above so that the normal distribution is used to approximate binomial distribution. So we know that NP, number of successes, is greater or equal to 5, and NQ, number of failures, greater or equal to 5. Both 58 and 42 are greater or equal to 5. So the claim the XOR method of gender selection increases the likelihood of having a baby girl results in null hypothesis HO DDR P equal 50%, and alternative hypothesis H1 P is greater than 50%. They work under the assumption that null hypothesis is true when population proportion equal to 0.5. 50% is 0.5. So the sample proportion of 58 in 100 birth, the result p-hat equal 58 over 100. So the sample proportion is 0.58. Now, since we know p-hat is 0.58, population proportion p is equal to 0.5. That's why it's always stated in the hypothesis in terms of population perimeter. P is 0.5, and we know Q is 1 minus P is also 0.5, and we know sample size is 100. We can use a z-score formula, p-hat minus P over square root of PQ over sample size. So it's 0.58 minus 0.50, 50 divided by square root 0.5 times 0.5 divided by 100, and this turned out to be 0.08 over 0.05. This is exactly 1.60. Okay, so we know that from when the z-score is between -2 and 2, and we know that this is the usual value. So z-score of 1.6 is not unusual; it's a usual value. So we know that 58 girls in 100 births does not seem to support. So this is the usual, it's happening all the time. Does not seem to support claim that XOR method increases the likelihood of having a girl, meaning more than a 50% of chance. And we have three types of the test. We have two-tail, we have left tail and right tails. Okay, so two-tail meaning the bell curve both the left and right tails' rejection region, critical region, occur at two tails. Left tail critical region only occur on the left tail, and right tail critical region occurs on the right tail. So the tails in the extreme regions are the critical values. So basically, that's what we call the extreme values. So typically, we reject HO if test statistics fall in the critical regions. Determination of p-values, critical values, affected by whether critical region is two tail, left tail, and right tails. So it's very important to make sure you have the right test, the label as two tail, left tail, or right tail. And either one of these is determined by the alternative hypothesis. That means H1 determines all of this. Okay. HO always has equal sign. H1 not equal to meaning it's two tail. So this indicates two tails. And if test statistics fall in each region here, left tail, right tail, then we reject HO. So those two tails are rejection region. You can call critical region or rejection region. Second test is the left tail test. Again, determined by alternative hypothesis. When you have less than, that means it's the left tail. Okay. Then left tail is the rejection region. We reject HO. Reject HO if test statistics fall in the rejection region. The third test is the right tail test. When each one has greater sign, that means it's right tail test, then the right tail is the rejection region. And it was defined by critical value here. Critical value goes here. Critical value separates usual values from unusual values. We'll talk about critical value, chapter 7. Here we have 3 common critical values for z-test. And for t-test, you have to look it up on table A3 using alpha and degree of freedom. The p-value, probability value, is the probability of getting a value of the test that is at least as extreme as the one representing in the sample data. So critical region in the left tail, p-value is area to the left of the test statistics. Critical region in the right tail, and p-value is equal to area to the right of the test statistics. Critical region in two tails, p-value equal to twice the area in the tail beyond the test statistics. So double the area because two tails. So now hypothesis is rejected if p-value is very small, such as 0.05 or less. Meaning this is alpha, right? Alpha is equal to 0.05. If less than 0.05, then rejected. It's highly unlikely. So the claim that axon method of gender selection increase likelihood of having a baby girl results in following null and alternate hypothesis, which stated a couple times already. So here p equal to 0.5, q equal to 0.5. Sample proportion p hat is 0.58. Sample size is 100. Then find the test statistic z-score. P hat minus p square pq over sample size. So 0.58 minus 0.5 over square root of 0.5 times 0.5 over 100. That turned out to be 1.60. Exactly 1.60. Okay, that's the test statistics. So if you look at, so now we know that this is right tail because on alternate hypothesis, right tail test. That means on the right tail we have the rejection region, critical region, rejection region, the right tail. And for z-score equal to 1.60, the area to the left from the table A2. From the table A2, we can find the area on the left. Area on the left must be 0.9452. And we want to know the area to the right, which is, okay. So area to the right will be p-value is 1 minus 0.9452. That turned out to be 0.0548. So you look up this z-score in the table A2, find an area to the left. And if you look at this area, this is greater than 0.5, greater than alpha. That means it's more likely this is usual event. So it's likely event, so it's bound to happen. So we know that we fail to reject HO. So conclusion here is fail to reject HO. These flow charts show you what kind of test we're talking about. If left tail, right tail could be two tails. And that's how you draw a bell curve and then visualize the area critical region on the bell curve. And the critical region, again, a rejection region is on the tails, either on the left tail, right tail, or both tails. Set of all values that test statistics that cause us to reject null hypothesis. So if test statistics fall in the rejection region, reject HO. If test statistics fall outside the rejection region, then we fail to reject HO. The critical value is any value that separates the critical regions from the value of the test statistics. The critical value depends on the nature of the null hypothesis, sampling distribution that applies, and the significance level alpha. Alpha is very important. For the axial birth hypothesis test, and the critical value and the critical region for alpha equals 0.05. Since in a two tail, that means in the right tail, so means on the right tail this area is 0.05, located on the right tail here. Area to the left is 0.95. And go back to table A2. Use 0.95 as area, go to table A2. You'll find a critical value z-score, which is 1.645. And we know that the test statistics z-score smaller than 1.645. So test statistics fall in here. So it does not fall in the critical region or rejection region. That's why we fail to reject HO. Z equal 1.60. Smaller than 1.645, so it's located on the left hand side of the critical value. So fail to reject HO. The p-value is different from the population proportion p. P-value is probability of getting test statistics that's unlikely. Okay, highly unlikely event, getting highly unlikely event. And P represents population proportion, it's population success rate. So it's different, has totally different meanings. Step 7, make a decision, reject HO or fail to reject HO. Depends on how if you're using the p-value method. If the p-value less than alpha, then reject HO. If p-value greater than alpha, then fail to reject HO. Less than alpha meaning it's highly unlikely, so you gotta reject it. Critical value method, if test is falling in the rejection region, then reject it. Otherwise, fail to reject. So p-value method, p-value less than or equal to alpha, reject HO. If you are greater than alpha, fail to reject HO. In critical value method, if the test statistics fall in the critical region, rejection region, reject HO. Test statistics does not fall within the critical region, then fail to reject HO. So for the actual baby gender test, the test has a test statistics of C equal to 1.60 and a p-value of 0.0548. Using the p-value method, we fail to reject HO at alpha level of 0.05. Critical value method, we also fail to reject HO because test statistics does not fall in the rejection region, so we fail to reject HO. Eventually, on step A, you state a final conclusion, address the original claim with respect to the context. Also, make sure that using the simple and non-technical terms to assess the claim. So for the actual baby gender test, there was not sufficient evidence to support a claim that XOR method is effective in increasing the probability, since we failed to reject HO. HO is P equal to 0.5. P equal 0.5 meaning probability of having a baby girl is 50%, probability of having a baby boy is 50%. Without using the method, that always happens. So this XOR method is not effective, right? If you put in a really simple language, XOR method is not effective in terms of improving the probability of having baby girl. This is what we call a simple and then non-technical conclusion. So reject it, if you're stating the conclusion as a reject null hypothesis, fail to reject null hypothesis, that's not good enough, because most of audience wouldn't understand what reject null hypothesis means. So always related to the actual problem or actual context, use a simple, non-technical language to address the original claim. Again, typically we do not use accept the null hypothesis because we're not proving the null hypothesis. We can prove the null hypothesis. Further reject says more correctly, the available evidence is not strong enough to warrant rejection of null hypothesis. So we typically just saying that failed to reject HO. Instead of saving accepting, right? I'm not using accepting now about this. So the last couple terms we try to explain here, type 1 error is the mistake of rejecting null hypothesis when it's actually true. So you're rejecting the true claim, then you're making a mistake. So that's why it's called type 1 error. We're using symbol alpha to represent the probability of a type 1 error. Type 2 error is the mistake of failing to reject null hypothesis when it's actually false. So you have false claim, but you fail to reject it. Again, you're making a mistake. So that's why it's called type 2 error. Using beta to representing the probability of type 2 error. So this is 2x2 continuum table give us the idea type 1 error occurs when we reject null hypothesis, but it's a true hypothesis. If we reject the null hypothesis and the null hypothesis is false, then this is a correct solution, a correct decision. If we fail to reject null hypothesis, the null hypothesis is true, then this is a correct solution, a correct decision. If you fail to reject the null hypothesis, however, null hypothesis is false, then you're making a mistake. This is type 2 error. Using probability of type 2 error is beta. Probability of type 1 error is alpha.